Okay, in class today we're talking about the fundamental theorem of calculus. The first fundamental theorem of calculus, because apparently calculus is very important and it has multiple fundamental theorems. Yeah, usually in my mind the first one's fundamental and the other one is less fundamental. Anyway, let's don't talk about that. The first fundamental theorem of calculus can be written in a number of ways, but it tells you that if we are taking the integral from 2 points, right, on this closed interval from a to b, okay, we're assuming that the function is continuous and differentiable on this interval, or this would not be true. Okay, if the function is not continuous, then we can't take the integral of it. Okay, so the assumption here is that your function is continuous on the closed interval from a to b and differentiable on the open, just like the IVT and the NVT and the EVT stuff. Okay, so if we have taking the integral of some function, f of x dx. Okay, remember this is the area underneath the curve of our function from the interval of a on the left side to b on the right side. What we do is we find its antiderivative, okay, where f is the antiderivative, and we evaluate it at the right endpoints, and we subtract the antiderivative evaluated at the left endpoint. Okay, and that's what the fundamental theorem of calculus says. Okay, so we're assuming then, of course, that f, right, f that f prime, okay, hang on, that is not right. I need to erase all that stuff. It's got to come out of my mouth right. Okay.
Did you pause the video?
We are assuming that this is the derivative of that. Okay? So big F is the function where little f is the derivative. In other words, big F is the antiderivative of little f. Okay? So that's what we're trying to say here, is that if this is our function, right, then this little one is the derivative. So when we anti-differentiate, when we are integraling, we are finding the antiderivative. Okay, so we will integrate, or we'll take the integral, we'll find the antiderivative. Let's write that. That sounds like a better thing to write. The antiderivative.
Of which one?
So f, capital F, is the antiderivative of little f, which means little f is the derivative of big F. Okay, so this could also be written as, right, if we have the integral, and this is now some f prime, that means we're going to evaluate just the function at your two x values of a and b. Okay, so there's a couple ways we can write it. We can write it as if we have a function and we're anti-differentiating, or we can write it as if this is the derivative, right, then this is the function, or the y values at each of these respective x values. You'll see it written like that too. Okay, so let's try and do a couple of examples and see if we can equate all of this stuff to our Riemann sums and accumulation.
Attached, Dave? Not for the video.
This is supposed to be a.
Good shit, Dave.
F of b minus f of a. The right endpoint of our integral minus the left point of your integral. Okay, here are a couple of examples with a connection to the graph. So we're going to look at this graphically like we did a little while ago with our Riemann sums, and we're going to try and connect that to our integral and the fundamental theorem of calculus. Okay, so first let's look at our Riemann something. We want to find the integral, or the area under the curve, because that's what an integral is asking us to find, from a left value of -2, so we're going to put in a vertical line here through -2, right? This is our left value of -2, and a right ending value of +1. So we're going to try and find the area underneath the curve and the x-axis, so we're going to find the area of this. Okay, now last week, when we were talking about accumulation or estimating the area under the curve, we would probably apply, in this case, a trapezoid. So So let's figure out what the area of this trapezoid is using our fantastic geometry trapezoid area formula. Okay, so this base on the left is 7 units tall, and the base on the right is 1 unit tall, and the height of our trapezoid is 3 units. Okay, so for the trapezoid, we have the parallel parts, which are your bases. So the y values in this case represent the bases of your trapezoid, and the height is the distance in between your parallel parts, which is in this case the x value. So the area under the curve, our approximation would be 1/2 of 7 plus 1 times 3. Okay, which is 1/2 of 8 times 3. 1/2 of 8 is 4. 4 times 3 is 12. Okay, so using our trapezoid approximation, in this case it's pretty dang good because it's a straight line. We can actually get the area. The area of this trapezoid is 12. So knowing that, let's come over here and apply the fundamental theorem of calculus. Okay, so that says we need to find and evaluate f at 1 and subtract evaluating capital F at -2. Right? Because you always go from your upper end point, your right hand point, subtract your left hand point. So capital F, which is the integral of -2x plus 3, right? The antiderivative of -2x plus 3, evaluated at 1, and the antiderivative evaluated at -2. Okay, so what is capital F? What is the antiderivative of -2x plus 3? Okay, so we can use our rule of antidifferentiation of polynomials for this. So -2, we have x to the first power, so we will add 1. 1 plus 1 is 2, and divide by that power that we just raised our value to. Okay, plus 3. And this is, of course, x to the 0, so our antiderivative will be 3x. So one set of simplification gives a negative of x squared plus 3x. Okay, so that is the antiderivative of -2x plus 3. So now let's evaluate this at +1. Okay, so we're going to plug +1 in here. So the negative of +1 squared plus 3 times 1. So +1 squared is +1, and then we make it negative. So -1 plus 3 is 2. So the evaluated value at +1 of our antiderivative is +2. Okay, minus. Now we have to do the same thing for -2. So the negative of -2 squared plus 3 times -2 is -4 minus 6, which is -10. So evaluating f of -2 is -10. Oh my goodness, look at what had happened. Minus a minus is a plus, and the interval is 12. The area under the curve of -2x plus 3, evaluated from -2 to 1, is 12, which is exactly the answer we got from doing our trapezoid over here. Okay, there are connections, believe it or not, and they are pretty fantastic. So the integral is an area. If we have a graph, it's pretty nice. If we have an equation, we have to anti-differentiate. Okay, so let's see if we can make some more connections here on this second one. This is now going from 2 to 5, +2 to +5. So we have +2 here and +5 there. Okay, so we're going to find the area of this nice trapezoid. Let's color it in so we can all see the trapezoid. Okay, so if we, using our amazing counting skills, we count that the left base has a 1 and the right base is once again 7 units tall. So this one should also have an area of 12. I don't think we need to calculate that again with the same numbers. But because it's below the x-axis, the area is negative 12. Okay, so that's the key with this, is that if we have an area below the x-axis, we now have a negative area. So let's see if that jives with our antiderivative, or with our fundamental theorem of calculus. So we're going to evaluate the antiderivative at positive 5, and we're going to subtract the antiderivative evaluated at positive 2. So remember that antiderivative was negative x squared plus 3x. So plug in 5 and plug in 2 and see if you get what I get. Okay, look at that result. The derivative evaluated at those 2 points is the same as the area of that interval. Fantastic. I love it when a plan comes together. Okay, so how about if we look at this one from negative 1 to positive 4? Okay, so now we have 2 separate intervals where one is going to be a positive area, right? This is a positive area here. And this one is going to be a negative area if we continue on going to 4. Okay, so these are just triangles, right? They're no longer trapezoids. We can do 1/2 of base times height. And it looks like the base is 2.5 units times a height of 5. So let's see, 2.5 times 5, that's got to be something. Is this 1, 2, 3? Okay, so we get 6.25 for... So if this is the red area, then this is a negative 6.25 if it's the red down here. And if the blue one is the positive, that's still 1/2 of the base, which is 2.5 times the height of 5, which is a positive 6.25. So we should get a net area of 0. Okay, we should have a net area of 0. So let's go ahead and do our fundamental theorem and evaluate our antiderivative at positive 4 and at negative 1. And let's see what we get. Okay, sure enough, our algebra verifies what we got graphically, that the area between negative 1 and positive 4 has a net of 0. Okay, so this is a fantastic thing that we're doing here with the algebra. We can, if you don't have a graph, right, so not all these graphs are as pretty as this nice linear one. They can be all kinds of crazy things. But to find the area between your graph and the x-axis, you take the antiderivative and you evaluate it at the top, or the top interval, or the right interval, and you take the antiderivative and you evaluate it at the bottom interval, and then you subtract them. Okay, that is what our fundamental theorem of calculus says today. Hopefully that helps and you feel smarter.